Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Hi class, welcome back to SIC2006. Today we're going to proceed with lecture 4. Before that, I'd like to recap on what we have done last week. So I showed you this diagram and I hope that you remember this well, that in the event where there is no applied magnetic field, the two states, the alpha and beta states, and of course this refers to the spin half example like hydrogen. Okay, so the two states will be degenerate, and as soon as the applied magnetic field is on, so you have the Zeeman splitting, and the energy is given by delta E is equals to alpha H bar B naught. And I do hope that you remember how we actually get to this equation. So you have the alpha spin state at the lower state and the beta spin state, and you have the quantum number minus half and plus half. I also showed you this diagram, the FID, which is actually the NMR signal, but because it's not visually easy to interpret this by the normal NMR users, so the time-based spectrum is being Fourier transformed, which is just a mathematical equation being transformed to the frequency base. And so you have here the spectrum, which is much more familiar and easy to interpret for the normal users. On top of that, I also shared with you the equation for the population of energy levels, and I'm going to share with you my version of the solution to the problems, to one of the problems that I gave you. Right. So let's talk a little bit on the nuclear spins with respect to what happened, when there's no magnetic field and when there's magnetic field. So the nuclear spin, as you know, they act like tiny magnets, as we've discussed before. So when there's no applied magnetic field, so what you get are the random organization of this. Well, that's quite what you call it's really contradicting, random organized. But anyways, you get the idea that the spin is going to be randomly arranged, and so what you get here, there's no specific direction that they're actually pointing at. But you will imagine that when there's an applied magnetic field, the spin, the nuclear spin is going to be like a normal compass needle, in which you have the direction in the z direction. So you have the compass needle being aligned along the magnetic field. But that's not the case with nuclear spins, because they have angular momentum and magnetic moment, and because of that, what's going to happen instead, the nuclear spins are going to actually precess. So precess is where it's actually going to circle around, taking the angle of a cone, and depending on the initial direction of spin. So if it's initially in this direction before there's magnetic field, so it's going to precess, taking the angle of the cone, right? And so if you have, for example, initially it's actually aligned horizontal to the field, so it's going to take the shape of the field. So so it's going to precess. Okay, so now the question is, are the spins going to precess forever? So clearly not, otherwise you won't have any NMR signal. So then what's going to happen is that it's going to go through this relaxation process. And there are two types of relaxation, namely the spin lattice relaxation and the spin-spin relaxation. Sometimes this is called longitudinal relaxation, and this is called latitudinal relaxation. So so this is going to take place, the longitudinal relaxation, such that because it's not going to be precessing forever, and because there's also other types of molecular motions. There's also rotation, there's vibration that's going on in the molecule. So the molecular motion will actually cause this fluctuation in this microscopic magnetic field. So then what happens is that it's not going to precess anymore, and so then it will start fluctuating. The nuclear spin will start the magnetic field starts fluctuating, and so instead of precessing, the nuclear spin will start wandering with an A, not an O. And so, but despite the fact that it's wandering, you can imagine that because you have an applied magnetic field and it's a strong field, so it is more probable that the nuclear spin is going to be oriented along the magnetic field, at least on average. So what you see here is exactly that. At thermal equilibrium, so the net magnetic moment of the nuclear spins are actually along the magnetic field. And so this is what we call the longitudinal relaxation. So if you can't remember, just imagine it's along the magnetic field. So it's longitudinal relaxation. Sometimes you will see in textbook the what you call the magnetization buildup versus that of time. So this is just that. This is just extra knowledge for you. But you would think that that's how you get the NMR signal. But the NMR signal that you get is not based on the longitudinal relaxation, because the longitudinal magnetization is almost undetectable by NMR. So spectroscopists thought of how to actually make the signal detectable. So instead of measuring the nuclear spin magnetization along the magnetic field, so the magnetization perpendicular to the field is actually measured. So this is technical electronic situation in which that you find that when the magnetization is actually perpendicular to the field, then it's detectable by the NMR. So then that involves some kind of programming which is actually installed by default in the NMR, in the program, the pulse program we call it. So the pulse program that is being programmed by the spectroscopies will actually command that the spin, the magnetization measured will be perpendicular to the field. And so then you have this it's still the same process. It's still going through this precession and so on, but then all of this is actually going to be, once you actually apply the field which is perpendicular to the field, so you will see that then it will actually align along this direction. And then when there is a relaxation build up in this direction, so that is the signal that is being detected by the NMR. Okay, now this is just an extra that that the relaxation process, it says that you have this the magnetization will actually relax based on the fact that all the spins will not be in phase. I like to actually give you an analogy on this. For example, if you have, and I will usually quote in the auditorium, if you have, for example, 5 clocks that you put in auditorium in class. For example, in the BMK, we have this auditorium. Okay, say you have 5 different clocks that you put just to make sure that everybody is on time. All right, so say initially the clocks will be, for example, at 12 noon. So the next day, after 24 hours, the clocks will still be at 12 noon. But eventually, you'll find that the clocks are not going to be, be having this exact synchrony. So you will see that one will be at 12 noon in a week's time. The other will be maybe a little bit lagging. Maybe it's still 11:59. So you see that the clocks are not reading the same. So this is the analogy that I give, that the relaxation that the transverse relaxation is because there is no exact synchrony between the precessing of the nucleus spin, and so it will be out of phase. They're not going to have, as in the clocks, they're not going to be having the same time, and that it's because of the battery of the clocks, but in this case, because they get out of phase, and eventually it will actually die out as an FID. Okay, so this is the relaxation that you see in the transverse relaxation, and that is the signal that you see in the NMR that can be detected. Okay, so this is what I said. So this is called the homogeneous decay, the loss of coherence of each other. So this is just an example of an FID. So and this FID is so there are actually a lot of experiments which is actually relevant to this. One will look at the what they call, for the spin relaxation, the time for that is T2, and the spin echoes. These are all the experiments that usually spectroscopists will use to actually understand the materials and so on. So I'm just putting this as an extra information. Now, the relaxation, how fast actually the spin will actually relax, will influence the width of the spectral line of the NMR. Okay, and so when you have a very long relaxation, that will give you a very sharp pointed signal, and if you have a very short relaxation, that will give you a very broad what they call broad line. Okay, so this is just one diagram. This is for an extra information. So you see that in the building up of the T1, the longitudinal, so the T1 is counted as 63% magnetization. Okay, and the transverse, the T2, when it drops to 37%, that is considered that 1 time constant of T2. So this is just an extra information for you. Okay, so so you see here the process of getting a signal involves first the relaxation, and then you will actually then start building up the longitudinal, and then it start flipping again. So it start building up and start flipping, and then this one will die out, and then it start building up. So this repetition of this is what gives you the NMR signal. So the more time you actually do this process, you're going to accumulate the signal, and you have a better resolution. Okay, so the relationship between the line width, so the line width of a signal and what you see, for example, this is an NMR spectrum. The line width is defined as the width at half of the height. Now the height is not this. This is just the frequency baseline. So the baseline for this spectrum is actually this. So you need to draw a line here, and so that's the baseline. So you measure the height of this, okay, at half of the height. So this is where the line width is actually defined. Okay, and so why are line width important? Because there's also analysis on the line width. From the line width, you can actually describe your material, and especially if you have some additive to your materials and you are calculating the concentration of the additive that you put, it may actually affect, depending on how much additive that you put in your sample, it may actually affect the line width. So you can actually do analysis on the line width. Okay, and as I said before, in terms of, for example, the liquid state, it usually has a very sharp line because it actually decays quite long, but for solid samples, you usually get a very broad sample. So solid state or liquid crystal state will give a very broad sample. Okay, so pretty much that's what I want to cover. So in essence, when you have a rapid decay of the transverse magnetization, that will give you a broad spectrum line, and that is usually for the solid or semi-solid. And a slow decay of transverse magnetization will give you a narrow spectrum line. That's usually for the liquid state. Okay, right. So I'm sure you can answer this question. Which of these involves a fast decay? So either A or B. That's something which is very obvious based on what I've mentioned earlier. So if you can answer this, that means you've been paying attention. All right, so that's all for today. All right, so I'll see you next week then. All right, bye for now and stay safe. Take care. Assalamualaikum warahmatullahi wabarakatuh.